Excellent. So good morning, everyone. First of all, I would like to introduce myself. My name is Dmitriy. I have actually two hats. On one hat, I'm a technical director at the Royal Institution of the Naval Architects in London. And another hat, I also am managing this interesting JoRes joint research project, which I hope will be quite interesting for you to learn about. So I was attending this the keynote presentation this morning, and I saw quite a lot of equations, quite a lot of deep dive into the CFD environment, and I thought, wow, so that's probably my presentation will be a little bit different, because even though we're here about CFD, about OpenFOAM, I don't think you will find any equation in my presentation at all. However, there is a good reason why I believe we should talk about this, especially in the CFD community. And the reason is validation. Sometimes we have to go outside of the equations, outside of the mathematical environment, just to look at the actual physics, the actual pictures, in order to be able to validate our mathematical representation. All right, without further ado, I would like to go ahead. So first of all, at the very beginning, I would like to say a few words about the introduction, about the motivation. So why we're doing this, why we're spending our time and money to do this. And I will start introducing the project. So first of all, you obviously know, so now there are quite a lot of challenges in the maritime, so we're talking about maritime business in here. So even though we had a 2 years pandemic around hitting us quite hard, so still the expectation, the forecast for the next couple of years is still positive. So we're talking about 2.4% growth in the maritime trade in the next 4 years. And obviously now, even now, on the latest report, which was published by Unistat, we're talking about the quite significant freight rates for the containers and the dry bulk. Obviously not that significant trade for the tanker, for the oil, but for the container ships and the dry bulk freight is actually coming up. And at the same time, we do remember the challenge about the environmental situation. So we have a target from the International Maritime Organization to reduce our greenhouse gas emission by 50%. It's less than 30 years. So that's kind of, we should keep this in mind that yes, so we do have some sort of pressure from the environment to do something to make our ship greener, more efficient, and so on. And this kind of message was also conveyed in the latest ITTC meeting. So that was in Shanghai in 2017. Oh, sorry, in Wuxi, not far from Shanghai. And even though in the ITTC, so this is the Towing Tanks conference, yeah, model test facilities coming together to discuss the model test things about how to make the physical towing tanks representations. Even in that environment, so they outlined that they need the advanced CFD plus full-scale data in order to get our procedures, our recommendation for the better ships more and more reliable. There is in development. So just last year, finally, International Maritime Organization, they acknowledge or they accepted the CFD as an alternative for the model tests for EEXI calculations. So up until that year, up until last year, the only kind of measure for the efficiency on the before the design stage was model test. So everyone knew about CFD. A lot of people rely on that. A lot of people fascinated about CFD. It was not industry recognized tool. Now, from last year, I must say, we are talking about towing tank and or numerical calculations. So this is very important step forward. And just about the urgency. So the compliance with EEXI is actually started from the 1st of January 2023. So we have less than 6 months to start doing something. And CFD is a great tool because now all the towing tanks, they're fully booked, so they cannot fit any further model test. So CFD is probably the very good opportunity to do that. But the key point in here, even at IMO level, they do recognize the challenge of validation. They said, yes, we do recognize CFD. We do love it. We do believe in this. But you cannot just use CFD out of the blue. So you have to verify and you have to validate this. And they actually talking about the verification either on the parent hull or the reference set of the comparable shapes. So basically, we need to have quite a lot of cases available in the industry that the CFD practitioners could validate their CFD with. So that was kind of a bit of background, only 3 slides, but I do hope those slides kind of create some sort of outline of what's happening. So let me just briefly outline the current situation, so the current challenges. First of all, the current approach, how it's usually done in the maritime industry, I'm pretty sure you know about this. So we usually start with a CFD. We do a lot of designs, a lot of optimizations with CFD, then we move to the model test, and then finally we build a ship. But even in CFD, we have quite a lot of uncertainties. So first of all, it's lack of validation data, as I just mentioned a minute ago, and also the best practices. So a lot of participants, a lot of practitioners, different code users, Star CCM+, OpenFOAM, Fluent, or ANSYS. So they're doing their kind of things, and there is no proper communication. So there are not so many things that we are discussing between ourselves. Once you do the model test, the next step, so usually how it's done, so out of the CFD, we just derive the best possible shape, and we still do the model test for this shape, the more traditional approach of the CFD validation. But again, in model test, yeah, there are quite a lot of uncertainties. The scale effect, obviously, you cannot satisfy the Fruits number and Reynolds number at the same time. The correlation allowance, every research facilities globally, they use their coefficient in order to scale up their model test data. And another challenge is energy saving devices. So those kind of correlation allowance, the coefficients, they mostly work okay-ish for the traditional hull forms, but if there is something very unconventional, energy saving device or weird hull form, so those coefficients are actually challenged. And in that case, so they might not work well for some cases. And finally, so once the vessel is built and we do the full-scale trials on this vessel, it's still quite a lot of questions. So the sea state estimation, the draftsmark readings, hull roughness estimation, so not so many people doing that. And then at the end, we still get only one curve, which is speed and power curve. So basically, we're judging about the performance based only one parameter, which is power. And in power, you know, like everything is there, you know, the hull efficiency, propeller efficiency, everything is in one single parameter. So in that sense, this is technique, what we are doing now, but at the same time, so there is some sort of detachment from each other, right? So basically, there is no some sort of global feedback loop in here in order to make this work properly. Just a couple of slides about the model test. So you know how it's actually operates. So we do the model test, we build the model of the actual vessel, and it's usually about 6 meters long, so this kind of size, and we run this in the towing tanks. This is an interesting slide. Well, I do hope it's an interesting slide. So this is the presentation from the industry project Refit to Save, which was done by Marin, the research institute in the Netherlands. And actually, they selected 2 test cases, vessel A and vessel B, with adducted propellers. And the model test prediction, so show one piece of data, they thought, okay, it's going to be like that. And then the sea trials didn't show, like in some cases, it was either minus 14% of monitoring, or it was just 0 on the full scale. However, it was clearly prediction of the model test. So basically, in this particular case, specifically for ducted propellers, the model test, it's not the good answer because the approximations, the predictions which are done by model tests, they're not 100% correct. Physical tests. To me, like in my personal attitude to that, so when I was working at Lloyd's Register before, and I done personally quite a few sea trials, I thought that can understand the performance of the vessel once you are staying on the deck or in the engine room or in the bridge of this vessel. However, there's still quite a lot of uncertainties, and the key of them, the winds, waves, current, and so on. So sometimes you're expecting the weather condition would be like that for your trials, and you ended up with these conditions. And then, so because the time is allocated for the trials, and you have to perform the trials in this condition. And obviously, your prediction might be not very accurate at all if it's in these conditions. So, yeah, I'm not sure you can see the, the title of the slide. So there is a procedure. So the industry recognized procedure for the for the sea trials. It's ISO 15 or 16. And this kind of, we have to follow this procedure in order to make our trials as accurate as possible. However, in this procedure, you know, there are some few bits interesting. So the wind and waves can be determined by visual observation, multiple experienced mariners. So basically, if 5 people stay on the deck, all 5 of us, we can check the wave height. And one person says 1 meter, another person says 2 meters, third person says 3 meters, but we have to use a single value. Which one, right? No one knows. And depending on the which wave height you are putting in the spreadsheet, your curve will be different, obviously. The second point, the difference between ship displacement, it should be less than 2%. However, if you're talking about, let's say, crude, very large crude carrier, or like the tanker, you know, the 2%, it's quite a significant displacement. And this 2%, you know, if you're just talking about the resistance, it will give you some sort of deviation on the resistance. Again, it's a quite uncertainty. And another paragraph, 7.3. Okay, if there is roughness, you have to clean this hull as needed. What does it mean, as needed? You know, if me as a superintendent see this kind of condition on the hull and said, it's fine, it should be all right, it should be fine. However, obviously the resistance of the vessel will be quite significant, right? So it's kind of a lot of subjective meaning and subjective discussions happening in this procedure, and we have to deal with this somehow. So in that sense, specifically, if we're talking about EEDI or EEXI, yeah, it might be identical vessels, sister ships, built by the same shipyards. But because of these factors, the speed power curves will be very different. Which kind of doesn't make sense, because for the owner, they might ask, hold on a second, I have 2 identical sister ships. How come I have 2 different performance characteristics of them? Doesn't make sense. CFD. That's probably the only slide I have about the CFD. So obviously, it's a very good tool. It can offer both scales, and we can do quite a lot of dive into what's happening with the flow and so on. But again, the only or the most cases for validation we have, it's again the model tests, which we don't take into account the scale effect. So we don't have enough data for the full scale validation, and that's kind of the challenge. This is probably the only publicly available curve at the moment. So in 2016, we ran the workshop at Lloyd's Register, and we asked participants to submit blindly the results for the actual ship. It was a general cargo vessel, and the participants did the results. So basically for them, it was a blind calculations. And then at the end, we came together, all of us, in a rainy day in Southampton in November 2016, and we just discussed these results. So you see quite a lot of participants. They under-predicted the curve, the orange curve, which was actually from the trials. However, some of them, you know, these points, they just spot on. So it means there is an opportunity, there is a possibility to predict the curve, to predict the performance accurately. If you have experience, knowledge. So that was one of the key outcomes of that workshop. And now having this in mind, so we are working on the global initiative. It's called the JoRes Joint Research Project. And this is the largest joint industry project which was ever run by Marin, the research institute in the Netherlands. Because normally for the joint industry project, we have about 15, 20 participants. In here, we have more than 40. And I will show you this slide in a minute. And the key point, this project is supported by IMO, International Maritime Organization, because they said we do need the reference cases in order to validate our CFD. So for this project, we have 3 vessels. One is actually already famous. It's the same vessel we used in the workshop 2016, the MV Regal. But now we have quite a different set of results. So we have like different measurements, new technologies, and so on. And 2 other vessels, it's a single screw tanker and the twin screw vessels. It's just for indicated. So basically, the more vessels we have, the better variety of data we have. So the better our predictions and the validation data will be. So this is the list of participants we have at the moment. And I think it's very good bunch of companies, because you can see there are key shipyards in here, let's say Samsung, Damen, Hyundai, DSME, the research institutes like Marin, HSVA, SSPA, and so on. Propeller designers, and Nakashima somewhere in here, yes. Class societies like Bureau Veritas, Lloyd's Register, and so on. So basically, this is exactly what we wanted to bring. So the different stakeholders with the different backgrounds, with the different ideas, sitting together and developing the benchmarks for the future CFD. Just in a, like one slide about the objectives. So basically what we want to develop out of this project, yeah, it's an industry recognized benchmark. So something which would be available for everyone, that everyone, the new practitioner or someone who just developed the new CFD tool, or maybe start doing the CFD business with the existing tool, they can validate their results again this case and make sure that they are doing not something like very crazy. So they are in line with other and the measured data. Obviously, the best practice and recommendations, and the key point, obviously, now we're talking about decarbonization, about the alternative fuels, and so on. But at the same time, we are together, for instance, one of the cases is we're working together with the Myers McKinney Zero Carbon Center, you know, the research institute which was established in Denmark. And they understand that in order to start working about the alternative fuels, you have to make your vessel efficient first, because you don't have too much money to spend on the methanol or ammonia if your vessel is not efficient. So let's focus on the efficiency first, make sure you get most of the efficiency, and then move to the alternative fuels. So that's kind of the message is being discussed now in the different levels of the maritime business. So I'll just, obviously I don't have too much to discuss in details about all aspects, but I would like to highlight like a key points why this project is very unusual. It's very different to other projects. So we do have 3D laser scan all our vessels. And you might ask why? Because usually the designers, we do have geometry, right? We do have the CAD files, which was developed in Rhino or whatever, right? For the propellers, for hulls, why do you need to spend time and money to do the 3D laser scan? As you know, they are different. To order this on the Korean shipyards, and there's some deviations with the hull, and it might be like, I wouldn't say half a meter, but it would be, might be quite a significant deviation. So that's why we have to make sure that we are calculating the actual vessel which was tested in the trials, and there is no deviation with the geometry. So that's why we do the 3D laser scan for all our vessels. Roughness. Sorry, I just holding the microphone, so maybe it was a trouble for the online speakers. To be honest, we might kind of open the Pandora box with the roughness, because once you're doing your validation and model tests, yeah, against Crusoe container ship, Moira tanker, model test propellers, you don't actually think or care about the roughness, because you're just assuming the object, your model, is hydrodynamically smooth. But once you're talking about the actual ship, 200 meters, with the belt seams, with the anodic protection, with the bilge keels, with the imperfections on the hull, you cannot ignore roughness any longer. You have to deal with it. And the challenge is we still don't know how to do that. So that's why one of the exercises that we're doing now is actually some sort of understanding of the roughness effect. And in order to understand, so we have to measure. So basically here, we're measuring roughness in a dry dock. So we put the vessel in the dry dock and we use the special sensor to get the roughness data. So that for the hull. We also use alternative techniques, so some imprints. It's like a two-component putty. You're just mixing this up, you're applying on the hull, and you get the imprint, and then you can send this imprint up, and they will give the full analysis of the roughness characteristics. And we do the same for the propeller. I'm not sure you can see it. We applied quite a lot of this putty in the different areas of the propeller in order to get understanding of what the actual roughness of the propeller. Because again, if the propeller is 10 meters in diameter, you cannot assume that it's smooth any longer. There is something there. And we have to quantify this. Model test. So as I usually, as already mentioned, so the traditional approach, we do the model test first, and then the vessel is being built. And usually what's happening is you do your model test at the conditions you think, craft, speeds, geometry, and so on. And then during the construction time, you know, the vessel might be slightly different and conditions will be different. And what we see, the trials conditions, they're never the same as the model test conditions. So it might be different drafts, different speeds, and so on. So what we do in the project, so we start with the actual trials. So we perform trials first. We know exactly the conditions of the draft, speeds, everything. And then we replicate these conditions in the turbine tanks. And again, for the turbine tank, we don't use this as design geometry. We use the 3D laser scan geometry. So we just matching kind of reverse engineering. So we're doing the model tests after the actual trials in order to match and learn more about the scaling effect. Propeller thrust. I mentioned a few minutes ago that at the moment, the only parameter that we are working with is at power, propeller torque, which includes hull efficiency, propeller efficiency, everything. In order to find out what's the difference between them, you have to measure propeller thrust, which is quite a tricky thing to do because the compression of the shaft line is very minor. It's like a few microns. So you have to determine this in a noisy, highly vibrating engine room in order to measure this. And we're working together with the Buff Instruments who developed this TT Sense, and this was applied on a few vessels in our project to measure the propeller thrust. And just a fun fact, accuracy of the sensor, it's just 25 nanometers, which is equal for 5 seconds of the air growth. So if you just count 1, 2, 3, 4, 5, your ear will grow for the just 95 nanometers, which is the accuracy of the sensor. Trials. I mentioned about the ISO 15 or 16 standard, which industry recognized standard, but still quite vague. In here, we are doing more because for our purposes, for the CFD validation, we need to have on the safe side. So we need to look deeper and with a higher level of accuracy. Specifically select a very good weather condition. So we're just trying to make sure there is no wave, significant winds and so on. We do perform, if we can, the trials in the loaded draft, which is again a challenge, because on the trials, on the delivered trials of the vessel, most likely it's a ballast draft. You cannot put cargo on the vessel in order to make the trials. But EEXI, its requirement, it has to be in the loaded draft. So what we done, for instance, for this tanker, we managed to convince the ship owner to fill the cargo tanks with the water and make a deeper draft, and made the trials with a deeper draft, with the design draft. It's a very painful situation for the owner, because now they have to clean all the cargo tanks, because obviously it's a salty water in the cargo tanks, which is not good. So it will cost quite a lot of them to clean this up, but obviously that's part of the agreement. We usually do quite a lot of runs, because according to the ISO standard, it should be like 3-4 reciprocal runs, so like 8. We usually do either 12 or 16 in order to increase the confidence in our runs. And once we do the PIV measurements, we usually increase. So usually the according to standard, it should be 10 minutes. We do it 40 minutes in order to make, but I will just have a few slides in order to make these PIV measurements. Have you heard about PIV? Particle, if you cannot see it in here, I just put some in hits. Particle image velocimeter. So basically, apart from measuring the propeller torque, which is power, we would like to know what's actually happening next to the propeller. What kind of flow? What kind of interaction of this flow with the propeller and the hull? And to do that, we developed you cannot probably see it properly. We developed a special tool. It's called PIV unit, which is, again, almost 6 meters long, with a weight 1,000 kilograms, so 1 ton. And we installed this unit on the tanker next to the propeller. And when we conducted the trials for this vessel, we actually measured the flow. So this is how it looks like next to the propeller. So there are 3 windows. Maybe I should use the mouse for the audience online. So 3 windows. In here, in the middle window, there is like a laser unit, which creates this laser sheet. And there are 2 cameras in front and behind, which measure the particles which are coming through this hot-lighted layer of the laser. That's kind of the idea. So that was the first ever installation of PIV unit outside of the hull. So this actually gave us a very good opportunity to rotate this and get as much data as possible, because the previous attempts of doing this was through the windows, tiny windows, and obviously you cannot get the full vision of the flow if you're just working through the tiny windows. In here it was fully outside. We could rotate this almost 180 degrees and get the full picture of the flow coming to the propeller. So these 2 colleagues of mine from Marine, so we are sitting in the noisy environment of the engine room. You see they have air plugs, and they're doing the actual PIV measurements on vessels. So usually PIV is done in a very controlled environment, in a towing tank. People are sitting with a cup of coffee, enjoying their life with the air condition, and doing the very, let's say, accurate measurements of PIV. This environment is very different. So you have to go back and forth with this stair, because it's like a tiny compartment in the engine room. But at the end, we got 6.5 terabytes of data. So now we are still post-processing this data. And then CFD part. So yeah, Mark and Hrvoje, they involved in this part, and yeah, I do appreciate their contribution. So we're doing quite a lot of interesting studies with the CFD about the grid-dependent studies, about the thrust validation, about the roughness analysis. So it's quite a lot of things happening in this area as well. So the key message, so if you go outside and later on someone asks, so what's the key message of this presentation? So what did you learn about this presentation? So the key message is like that. Once you do the model tests, in here, in this project, so we do the model test after the trial. So we do the reverse engineering. And we do it in different facilities. So if someone is doing something wrong, we don't repeat this error again. So we do it in the different facilities. So the one model test in Norway, another was in China with the same model, by the way, and so on. For CFD, so we have the validation data development, and we're just developing the best practices, how to run CFD with a highest possible standard. And full-scale experiment. So we have the sea-state assessment with a buoy. We have the accurate draft measurements, thrust measurements of the actual vessels, and PIV measurements of the flow. And the most importantly, so this kind of looped. So we do this for the same geometry, for the same conditions. So basically now you have the opportunity to cross-check, to learn how it's, because unfortunately, none of these methods, they're 100% accurate, right? So you have to have the fusion of all of them in order to better understand the reality. And the concluding remarks. So in here, we're just doing the industry recognized benchmarks for the CFD validation. And that's why the key message of why it's probably important for this audience, because we need the real data, the actual roughness data, the actual measurements of the vessel, on the vessel, from the vessel, in order to validate our CFD. This will create the opportunity to learn more about the energy efficiency. Maybe with this kind of set of validation data, in a few years' time, we develop completely new hull form, or completely new propeller, or energy-saving device, which give quite a good gain for the energy efficiency. Just one of the examples. So in 2015, the group of researchers from DNV, the German class society, well, now it's Norwegian German class society, they made an interesting study. So they took the initial hull form and they used the artificial intelligence to run the optimization process for the hull form for, I think, for few specific speeds. And they done 37,000 iterations. So they just considered 37,000 hull forms in order to get the best result. And they ended up with the final hull geometry. Would you imagine the gain, the difference of the resistance between the final and the first? What do you think? Few percent? 3%? 1%? 2%? The answer is 26%. I can send you this paper if you're interested. So the gain was 26%. So the final form, hull form, was 26% better than the previous one, the original one. It still might be speculation because the initial hull form would be pretty bad, and that's why they gained such a big difference. But anyway, that's a very impressive numbers. So that's why this CFD, the optimization processes, will give create a new opportunities for all of us just to develop more energy efficient ships. And this is, I want to show that. So we do have support from IMO. So we had a presentation at IMO a while ago, and you see we're sitting on the assembly room in IMO next to the chair of the Secretary General and presenting our project. It was like a few years ago. But anyway, so that's my final slide. I would be more than happy to answer questions if you have any. Thank you very much.
For those online, please put your questions in the chat, and we will start with any questions in the room. So for the benefit of the audience, Dmitriy, can you please repeat the question?
Yes.
Thank you, Dmitriy, for the very nice and useful presentation. Just one thing, we talked about it yesterday, but I think that it's good for people to hear. What about the particles used for the PID? Because when you know this, they are controlled.
Yes, yes. So the question is about the particles which are used for PIV measurements. It's a very good question, because once you start exploring the idea of using PIV, the tool which is mainly used in the labs, in a very good environment, in a perfect environment, very controlled environment. So once we start to explore this idea to actually put it in an actual vessel, not a research vessel, the cargo vessel, tanker, which was not designed for that. A lot of scientists and researchers are skeptical about this, saying it will never work. What never work is these particles, seedings. Because once you do it in the towing tank, you have to artificially create the seedings in the water. So you have to drop something in the water in order to be able to reflect your laser on. And this amount of particles you're actually dropping in the water, yeah, it's kind of, it depends on the researchers. You know, someone drops, you know, like a few minutes before the trials, just literally dropping something in the water in order to make it happen. On the actual conditions of the sea trials, obviously you don't have this opportunity. You cannot drop anything in the water. And that's why a lot of people are quite skeptical about PIV will never work in the real conditions. But apparently, the nature is smarter than we think. In the actual seawater, there are so many particles by itself. Sometimes you can even see like shrimps, you know, coming through and the laser actually catch this, you know. So obviously it's probably a bit of, you know, bigger particle, but it catches. So there are a lot of things in the actual water, seawater. And apparently we had a very good, so now we're analyzing the data and the preliminary results are already available. So it's a very good quality of the data from the actual trials. And some people, they're even joking that apparently the salty water of the actual sea is more suitable for PIV rather than water in the towing tank, which with artificial seedings. In that sense, it's very kind of counterintuitive conclusion, but apparently PIV might work even better in the actual conditions rather than in the towing tanks. You don't care about seedings at all.
It's not PIV, it is shrimp IV.
Shrimp IV, yes.
Any more questions?
You talked a lot about various levels of uncertainty in what you're doing, so different from the whole length of ship displacement, roughness,
Yeah.
geometry difference, and so on. Do you have, are you guys developing methodologies to determine sensitivities and uncertainties so that you can see focus? That, you know, cause the biggest differences.
So your question about sensitivity analysis, sensitivity studies.
Yeah.
Yes, that's exactly what we are trying to do. And obviously we are trying to do this not only for the CFD part, because in CFD, as I said, so we have the variety of participants with different codes, with different skills, with different approaches about how to build the mesh and so on. Yeah, so we can do the sensitivity analysis on the CFD part. But we would like to also have some sort of sensitivity study on the actual measurements. And the good example, for instance, for the drafts measurements, you know, so once you do on the actual vessel, you have a draft, you have some sort of, you know, so you measure in the draft. So sometimes you're using your naked eye or like a GoPro camera in order to record the drafts. And obviously the water fluctuates, so you have to analyze this data. And in order to address this uncertainty, this kind of subjectivity of the readings by a naked eye of single person. So for instance, for the tanker, it was 2 independent researchers independently looked at the data that we collected with the cameras, yeah, and they ended up with a 2 independent set of results that we could compare and see whether there is like error, there is a mistake, there is uncertainty and so on. So basically, we're just trying to do everything as accurate as possible in order to make the results more or less objective. For the roughness measurements, what we done with the tanker. So what I was done, I repeated the measurements twice in the same areas. So the same sensor, you know, like 1 hour between the readings in the same areas, have 2 separate sets of data. Obviously, they're not identical, but at least so we get some sort of uncertainty analysis on that. So very good question, and we're just trying to address this.
Okay, well, thank you very much. Let's
Thank
move
you.
on to the next presenter.
Okay, so good morning to everyone. I am Barbara Rinauro from the University of Naples, Federico II. I would like to thank Professor Jasak and Dr. Horvat and all the members of the organization for this very interesting workshop. Today, I'm here to present a work I carried out with my tutor, Professor Begovic, and with Professor Jasak and Dr. Gatin. And the work focuses on CFD simulations for surf riding phenomena. I will first describe the physics of the phenomena, then which has been first studied with a one-off mathematical model. And then I will describe the set of CFD simulations, concluding with results and discussions. So what is surf riding and broaching phenomena? Surf riding occurs when a ship is sailing in following to quartering waves, and with the ship speed lower than wave celerity. In this condition, the ship may be caught by the wave and start sailing with the same speed as wave celerity. In this condition, surf riding equilibrium occurs. In this condition, the ship is unidirectionally unstable, and in an uncontrollable turn to beam position may occur, which is called broaching, which may lead to capsize. Since the surf riding is a precondition for broaching, which has a more complex dynamics, surf riding study is used to detect broaching vulnerability. The physical phenomena of surf riding can be first schematized with a one-off surge motion equation in regular waves. The equation considers the equilibrium of the forces acting on the ship in the forward speed direction. The forces are the resistance, the thrust, and the wave force. The surf riding equilibrium is reached when the difference between the resistance and thrust go to the equilibrium with the wave surging force. The resistance and thrust is represented by the green curve, while the wave surging force is represented by the red sinusoidal curve. During the surf riding equilibrium, two types of equilibrium may exist. Stable equilibrium when the wave throw is at midship, and unstable equilibrium when the wave crest is at midship. Rewriting the one-off equation in terms of surge, displacement, velocity, and acceleration, the equation becomes a second-order nonlinear differential equation. This equation cannot be solved analytically. Therefore, the system's behavior is studied throughout the nonlinear dynamics procedure. The solution of surge and velocity, surge displacement and surge velocity made it possible to represent for a phase plane representation. And the calculation of stable manifolds with a calculation of the stable manifolds. Two conditions have been identified. The first condition is when surf riding is in between the first and the second threshold. In this case, depending on the initial conditions, both surging or surf riding motions can be possible. And the surf riding motions are delimited in the domain defined by the stable manifolds. The second condition is surf riding over the second threshold. In this case, whatever the initial condition, the only possible motion is the surf riding equilibrium. The change in the system behavior in this case has been obtained increasing the wave height, but other control parameters to observe the systems changing, system behavior changing are the propeller number of revolution and the wavelength. The more relevant and dangerous cases are the ones which consider a wavelength similar to the ship length with ship speed similar to wave celerity and with high wave steepness. After studying the phenomena with a simple one-off approach, CFD simulations have been performed to analyze the complex phenomena in all its aspects. CFD simulations have been carried out with the Naval Hydropack based on OpenFOAM, developed by Professor Jasak, Dr. Gatin, and Vukovic. The numerical models used to describe the incompressible Newtonian turbulent two-phase immiscible fluids is described the Runts equations. And here I reported the formulation for the combined continuity equation and momentum equation for air, water, and interface. The free surface modeling, for the free surface modeling, the interface capturing is treated with redistance level set transport equation derived from the phase field equation, which unites the unboundedness of the sign distance function of the level set method and preserves the hyperbolic tangent profile from the phase field method. The implicit treatment of the free surface jump condition is treated via ghost fluid method, which overcomes the numerical errors found in conventional methods by imposing the interface kinematic and dynamics boundary conditions and accounting for discontinuities in the density field. The wave modeling is obtained throughout a double decomposition, a solution decomposition achieved via Swen's method, which decomposes the wave field into incident and perturbated components, and a domain decomposition which is achieved via relaxation zone, which is an implicit approach which forces the generated perturbated field to vanish in the far field boundaries. From the picture, we can see that the red zone, in the red zone, the relaxation zone, the wave returns to its actual profile. In the blue zone, CFD calculation is full, and in between, we can see the blending zone. The partial nonlinear differential equations are discretized by the finite volume method in two steps: a solution domain discretization divided in time and in space, and an equation discretization which requires that the governing equations in integral form are satisfied over the control volume around a center point. Finally, the turbulence closure is achieved via two equation eddy viscosity models described as the K-omega shear strength transport model. Together with the numerical models, the physical models were the hydromechanic couplings, which combines the fluid dynamics and mechanical rigid body motion. The wave field was described by the linear wave theory, since only regular waves were simulated. And the propeller action was introduced, accounting for an actuator disk patch from we can see from these images, to which pressure jump interface was associated. So, surf riding occurrence has been studied for this parent hull of the systematic series D by Krachting Jakobson. The CFD simulations have been carried out at full scale, and the hull was scaled at 90 meters length. From the figure here, we can see the dimensions of the domain of the CFD domain and the refinement regions around the hull and around the interface in order to get a good results. The simulations were carried out considering only half of the domain, since the motion is symmetrical. The first set of simulations were carried out in calm water self-propulsion conditions in order to validate the setup of the simulations. Therefore, the ship was free to heave and pitch. and resistance and thrust values were analyzed and compared with experimental data available. From the graphs, we can see that the two approaches are in good agreement. Therefore, once the setup was validated, simulations in regular following waves were performed. Although CFD simulations are time-consuming, especially in surf-riding conditions when the encounter periods are very long since encounter frequency tends to 0, the advantage of CFD simulation is that the physical phenomena can be studied with great precision and analyzed in different aspects. In fact, we to observe and identify the surf-riding equilibrium, we used different approaches. The first approach was to identify and observe the motion of the ship in waves. From this video, we can see that the ship is in a surf-riding equilibrium. In fact, the ship starts sailing with ship speed lower than wave celerity. Then she got caught by the wave and starts sailing with the same speed. In equilibrium, surf-riding equilibrium. We can even appreciate here the relaxation zone where the wave turned to their theoretical profile. In this case, simulations were run with 3 degrees of freedom. The ship was free to surge, heave, and pitch. Another approach to identify surf-riding equilibrium was throughout the study of the tendency of the velocity. If the ship speed, the blue line, oscillated in time, surging condition was identified. When the ship speed reached the wave celerity and continued with the same value, surf-riding equilibrium was observed. Another approach was analyzing the phase plane. In fact, in surf-riding equilibrium, we can see that the phase plane trajectories tended to a fixed point. Moreover, throughout the analysis of the variation of the forces, we could identify surge motion when the forces oscillated in time, and surf-riding equilibrium when the force reached a constant value and went to the equilibrium. So, in order to have a comparison between the forces obtained by Wandt model and the CFD modeling, we performed a decomposition of forces. While the Wandt mathematical model has resistance, thrust, and wave force separated in its development, the dynamic equilibrium of surf-riding simulation is given by the inertial force, the total force in the x direction, and the propeller thrust. In this case, the total force in the x direction includes both the total resistance in waves, the added resistance, added inertial moment, and the wave force. In order to have a fair comparison between the forces, the total resistance in waves has been obtained subtracting from the total force in the x direction the wave force, which has been calculated by Hydrostar, which is a 3D potential code. Therefore, resistance and thrust forces have been compared. The differences we see between the resistance curves are due to the fact that CFD includes the added resistance due to wave, while Wandt approach considers only calm water resistance. And the difference may be attributed even to the variation of the wetted surface and wave force changes under the actual wave profile, which is only considered in the CFD simulations. The difference between thrust may be attributed to the different inflow velocity, since the wave field has been taken in consideration only in the CFD calculations. So as a result, we compared the one-off limits with the occurrence of surf riding in CFD simulations. In this framework, the one-off approach has been used as a primary tool to define starting setup case and starting points from which simulations, CFD simulation have then been performed. The cases ran were with wavelength similar to the ship length, with fruit numbers from 0.3 to the service speed, and with increasing wave heights. We can see that one-off limits defined by these curves are more conservative, since surf riding occurrence in CFD simulations appears at higher wave heights. This is due since CFD simulations include all the non-linearities not included in the one-off approach. It is worth to underline that for wavelength lower than ship length, no surf riding has been observed in CFD simulations up to wave heights equal to 5.5 meters. This can be explained analyzing the dynamic pressure distribution around the hull. We can see that for wavelength smaller than ship length, the pressure at the bow is greater, which induces a greater resistance and less likelihood the surf riding equilibrium. Concluding this talk, this work presents the application of the surf riding simulations for the study of a complex phenomena, which is surf riding. After a preliminary study done by one-off approach, which is more conservative but very fast, with CFD simulations, we had the possibility to study the phenomena in all its complexity, analyzing, considering all the non-linearities due to the waves and the hull water interactions. And it was possible to analyze the phenomena from different points of view, analyzing the forces, the velocity, the motions, and the pressure distribution. Last but not least, from time series obtained from CFD simulations, phase plane have been reconstructed to identify surf riding equilibrium in the same manner as the one-off approach does. So CFD is a powerful tool to analyze complex phenomena in all its aspects, and CFD gives the possibility, moreover, for repeatability of the simulation of the cases running, and the possibility to run full-scale simulations. For future works, we aim to simulate surf riding equilibrium, even surf riding occurrence in irregular waves, getting closer to what is reality, and simulate and carry out simulation in 6 DOF of freedom to observe the broaching phenomena too. Thank you for your attention.
Thank you very much, Barbara. Again, for online attendees, please put your questions in the chat, and we can start with some questions in the room.
I have 2 questions. I'll start with one. With the first, and then... Yeah, thank you very much, Barbara, for your presentation. I have 2 questions, and I will start with the first one. So I think this kind of situation is more relevant for the smaller boats, right? So once you actually, a lot of people, they might experience this on the yachts or the motorboats and so on. However, in your case, you consider the 90 meters vessel. So are you thinking to kind of to scale it down to the smaller boats? Because it's more kind of frequent situation for the smaller boats. See what I mean?
Yes, I see what you mean. And okay, so this condition, yes, is more probable for small boats, but it depends even on the wavelength, not only on the velocity. So when wavelengths are similar to the ship length, this condition may happen at the same way. So we scaled this particular boat to 90 meters length because it's a naval ship and typical of typical of the 90s, and so we made the situation like a real.
So basically, the vent plate length for your case was about 90 meters as well, right?
Yes, yes.
Oh,
yes.
okay.
So
okay.
we are not thinking about scaling. Otherwise, it won't be close to reality because those ships have been tested in experimental test with 6 meters length. But real ships are long around have lengths around 90 meters length, and so I hope I answered.
Basically, your recommendations, which are you develop for the 90 meters vessels with the length of wave 90 meters, will also be applicable for the smaller boats, let's say 10 meters boat with the wavelength 10 meters, right? Because it will be the comparable situations. Is that correct? See what I mean? So basically, if you have your case with a 90 meter vessel,
yes.
and the wavelength is 90 meters in your case.
Yes.
Yeah.
Okay. Yes.
Yeah.
So
if there's like a
scale,
practical situation, the boat is 10 meter. Yeah, 10 meters, and the wavelength is 10 meters. So basically, then you can apply your recommendations for this boat as well.
Yes, they are comparable if you both scale ship and length. Yes.
Excellent. And the second question, just a bit practical one. So obviously, you look at this case from the CFD point of view about the broaching effect and so on. But would you think about the practical recommendations for, let's say, captains? So if you are actually in this situation, what should you do in order to avoid the broaching? So I don't know, to increase the speed, to decrease the speed, to change the course, or something like some practical recommendations. So are you thinking to develop something like that?
Okay, so this phenomena is included in the second generation interstability criteria, which have been developed since many years, and they have become they are finalizing in these years. And this phenomena has been studied very much. And for answering to your question, other than evaluating a ship vulnerable or not vulnerable to surf riding, operational measures have been developed to help the masters in this difficult situation. In fact, depending on the loading condition and the wave conditions, the sea states, there are two operation the master can apply to avoid these situations. The speed can be lowered to avoid the surf riding condition, and the heading can be changed since the surf riding is more likely to occur in following or quartering waves, but not in the other headings. So yes, practically lowering speed and changing heading to avoid surf riding conditions. Or sometimes it's paradoxal, but sometimes if the ship is faster than the wave, so increasing very much the ship speed, of course, it depends on the kind of ships. Most most for small boats. Increasing very much the speed, this can lead to the avoidance of surf riding, because the ship is faster than the wave and the wave cannot catch the ship. So it depends on the types of boats and on the climate change, environment.
Thank you very much, Barbara. Any more questions from the room? Okay, so let's stop it here. I will do the next presentation. I assume you stopped sharing the screen, right?
Yes, okay.
Thank you, Barbara.
Thank you, bye.
Okay, so I would like to talk about Naval Hydrodynamics CFD and connect to the previous two presentations, which basically showed us how to do these things properly. There are several contributors to my slides, so I apologize to Sanyo for ruining a part of his presentation. He will do his presentation properly in the next round, and I will also speed up a little bit to make sure that we can catch up with the time. So I have spent quite a lot of my time trying to do conventional naval hydrodynamic CFD, which Dmitriy told us doesn't exist before the 1st of January 2023. And the points about doing that was, number one, we were not simulating ships, we were simulating models in towing tanks. And the way that this was justified is, this is where we have the data. The second thing is, as you heard again from Dmitriy, the scaling is a problem, and using scaling from the towing tank on CFD results just doesn't sound right to me. And the third aspect was, we have the problem of Froude number, which governs the waves, and Reynolds number, which governs viscous resistance, and which is in fact dominant for big ships. So you can have something like 80% of the drag being viscous drag and 20% being foam drag. And we are messing about with the scaling. So the credits go to Ino, Sanyo, and Andro Bakica, in this case, all three of them from the University of Zagreb, and using the Naval Hydropack. So let us just give you a bit of background of the things that really worry me. Okay, so one of the last slides from Dmitriy was a ship sailing into the sunset on a perfectly calm seas. So if you could please do that to all the ships, that would be a great improvement in emissions and energy consumptions, but we can't do that. So we are now capable of doing CFD modeling of a ship in waves, as you have seen in Barbara's presentation, but even those waves don't look real. So the real waves are irregular sea states, which are fundamentally stochastic. And what we are trying to do is to do a deterministic simulation or deterministic evaluation of resistance, power, and all the other parameters. And for me, this is a big problem, because when you drive a car on the motorway, you can assume that the forward speed of the car is relatively small compared to the wind speed or turbulent fluctuations. So this stochastic element gets washed out. With the ships, when you get hit by a wave, you know it, and it has got a significant effect on what's going on. So the model is nonlinear, and what should we really be doing? Okay, so that will be the second part of the presentation. And the first part of the presentation is, now that we got over this obstacle of, can we even do anything useful with CFD for naval hydrodynamics? What are the actual requirements from the people? So up until now, I was really proud of the simulation of this kind, where you have a nice hydrodynamic shape with the rudders. We use the immersed boundary to move the rudders and PIV controllers to steer the ship in the direction of the course. And I very proudly presented this result about 3 years ago. And when you speak to the actual ship builders, they don't care. They have a different set of problems, which is what we are talking about. So let me just show you a few movies of what real naval hydrodynamic CFD looks like. So the first thing is, there is no flat seas, there are waves. And here is one of those simulations of what the ship is doing in waves. And you will see that this is quite a big mess. Okay, you will also notice that my ship has got a bulb, and the bulb was designed for calm seas. Well, no. Okay, is this bulb doing what it's supposed to be doing here? Is it reducing resistance? How does the effect of the bulb change with the variation of the parameters? All of these things are questions that we need to answer. Okay, so the next one that I have is the one that I tried to show yesterday, and it is about spray rails on a full-size model. So if you look here, there will be a sort of bump in the form of the hull, and the idea is that you don't get droplets flying into the air, but actually rolling over. And this is one of the improvements that we can do with CFD, because in a model, you're going to have a model scale simulation, and capturing the effect of the spray rail is not that easy. So if you take conventional ship models in a conventional towing tank, water will be flying everywhere. Okay, so this is one of the reasons why we should be doing full-scale CFD, and this one is different from the previous one because the hull is in the planning condition, meaning that the pressure is holding it outside, which caused quite a lot of problems. For those of you who are experts in naval hydrodynamics CFD, in this simulation, we don't have problems with ventilation and other issues like that, because it took us a few years of CFD experience to learn how to make sure that the ship sails in the water and you don't get air under the hull. Now, the third one is very instructive because both of these two first hulls are really beautiful hydrodynamic shapes. And look at this one. Okay, so this is a roll-on, roll-off car carrier, and the bow wave doesn't look pretty. Okay, in fact, this is the real requirement, because we are sailing a ship with the big hydrodynamic free surface instability in front of it, but this is the form that people are designing and sailing, and as you can see, it is nowhere near hydrodynamically efficient. So I'm hoping that one of the optimization procedures that Dmitriy mentioned earlier can tidy this one up. Okay, so this is sort of 1.5 generation beyond the things that we have been doing so far, because suddenly we are doing full-scale ships. We are doing things that are not hydrodynamically optimized. We are doing waves, and we are doing secondary effects. And we are also crying about issues like what is the surface roughness, etc. Okay, so the next set of results really comes from Sanyo's work, and it is to do with propulsion. Okay, so one of the problems with propulsion is the difference in timescales. So you're going to have a rotating propeller with tip vortices, with turbulence effects, etc., hitting the rudder, which here it's still missing. And we have to worry not only about the efficiency of what this assembly does, but also about vibrations and loads that will happen there. So the kind of data that we want to get from CFD looks like this. So this is the propeller plane velocity contours. And as you can see, this influences your propeller performance. In other words, this is where the money is. This is the efficiency part of the job. And we have to be able to deal with this kind of simulation. But at the same time, I want to know how the ship behaves in waves. And that's not trivial at all. Now, on top of all of this, I'm going to show you one piece of what Andro Bakicaj has been doing, and that is related to energy-saving device. So the idea of the energy-saving device is that you put pieces of hardware upstream of your propeller in the money region of your ship and improve the flow field hitting the propeller. And here is a little example of what this looks like. And as you can see, there are 3 fins that they are not uniformly set up in space as you would expect. And that's because the propeller has got an orientation, okay? And the second thing is, just try and think about the scales. So if this is a full-size ship, this propeller is going to be 9 meters of diameters, which means that you have good 3-4 meter thin fin sticking out into the water right in front of the propeller. Okay, so Dmitry, please correct me, but the power that you're going to be submitting via the propeller to the water will be 15, 20, 30 megawatts. Okay, so this is a very serious fluid-solid interaction problem because the console that you see has got a relatively low natural frequency, and you have to make sure that you don't excite it close to its natural frequency because it's going to break off. So on top of the stuff that we were capable of doing before, now we have to include energy-saving devices, full propeller geometries, or a simplified propeller geometries. And on top of all that, we need to calculate the fluid-solid interaction between the components. Wow, this is a serious job. So what you can see here at the bottom is the coupled fluid-solid interaction between the vortices caused by the flow that we need to have here because of the energy-saving device, and the stress loading, okay, I think this is the von Mises stress, in the material structural model of the energy-saving device itself. Keep in mind that this thing is about 3 meters long, and it is not a solid piece of metal. So it will have an internal structure with ribs, etc. And it is being excited by the flow field, which involves vortices rolling off of my energy, or of Andros energy-saving device, and then going into the propeller plane, which is where I want to optimize the flow. Well, based on all this, I'd much rather do external aerodynamics around the car because this is such an easy life compared to this. So let me give you one more level of complexity. You have a 3 meter long console sitting in front of the propeller, which is submitting 15 megawatts of power to the water. And the propeller is rotating at, I know at model scale, it's about 12 revolutions per second. Here it's going to be about 100 RPM. And you carefully worry about natural frequency of the ESD being away from the natural frequency of the rotation of the propeller. And then you hit one of those waves from Barbara, and the ship does boom. Okay, what's the natural frequency of that? So in fact, there is a lot of parameters that we have to worry about when we do this sort of simulation. Okay, so let me get to the last point, which is going to take a bit of time, and that is the operational load. So imagine that we have a perfect naval hydrodynamic CFD code that you can perfectly trust. And I want to calculate a load on my ship structure, or in this case, that little piece of ship structure up here, which is the breakwater protecting the containers on the ship, okay? This one is called Skybench, and look at the size of it. 400 meters, 383 meters, and 212 tons of 212,000 tons of weight. Okay, so a ship like that will have about 20,000 containers on it. And the thing that you're going to do is you're going to put it into the waves. A piece of advice from the people in the know. When this ship is 30 years old, you don't want to be on it. And the reason for that is that unlike ships that are 50 years old, the lifetime of this ship is limited by the fatigue loading. So I need to calculate what is the fatigue load going to be on a ship like this. And I have the tool for which I assume that I can calculate the stress of a ship in waves. Yes, but which wave? Okay, the ship is going to be hit by what, about 1,000 waves in a 3-hour period of a 3-hour storm simulation. So over his 30-year lifetime, I cannot tell which waves are going to do damage. What I can tell is when Dmitriy gives me perfect sailing conditions, I can make the ship much lighter. So my first question is, how do you decide which wave to use to hit the ship? And here we have something called the relative wave elevation, which is the dominant load parameter, which basically says your ship is going to pitch in the waves, and the waves that worry you are the ones where the water comes on deck. Okay, so based on that, we can calculate the hydrodynamics coefficients, but guess what? Not with CFD, because you have to do so much simulations that we will use potential flow software like Hydrostar from Bureau Veritas. And after that, from the loading condition, we have to pick a wave. And there are two criteria. The first one is called the regular equivalent design wave, which says find out where the loading is worst, and then create regular waves to hit that ship and carry it in order to calculate the loading. Well, that's sort of okay, because doing a ship in regular waves is much easier than doing a ship in irregular waves. But I have this problem of resonance, because if I hit it on a regular wave train, the ship is going to respond in a certain way. So the other one says you're not allowed to have regular waves. You have to have an irregular wave packet, which is the representative of the loading. And that's called the response condition wave. And again, it's got a bunch of conditions. So what you do is you go through the definition of the design wave from the wave encounter period and the wave height. And you have to find out which one is important. So from a map like this, you find that the contribution to the long-term value of the load is going to be around here. Okay, so those are not the highest waves. In fact, they're pretty high, but it is the encounter period of the wave that matters as well. So now that we have picked one of those, we can design the CFD mesh to calculate the kind of things that we need to do. And again, this is not trivial, because we are trying to dimension this breakwater. The water line is going to be down here. The amount of water that we are going to get on deck is going to be relatively small. And in fact, it is so small that we have to use special numerics, geometric VOF, isod vector, in order to capture the interface in the impact region. So here's a bunch of pictures for a regular equivalent design wave. And what you can see is there are regular waves hitting this ship, and the ship pitches so much that the nose ends up in the water. But take a look at this graph here. Okay, force in the x direction between 3 10 to the 7 and 5 10 to the 7. Well, that's almost a factor of 2. Okay, and this is pure uncertainty of hitting the wave with the regular wave that I have picked out of a load condition that I have imagined. Okay, well, that's not very accurate. For the response conditioned wave, I'm going to have a wave package which hits, okay, so here you have the map of the wave package. And again, I'm going to calculate the force. Guess what? The difference in the maximum force is more than 50%. So which one do I use to dimension things? And also notice that this is a 400-meter beast that needs to live for 30 years. Okay? So in spite of the fact that we have all of these tools that are designed by experience, very much along the line of ISO 15016, I think we have a very, very long way to go before we can use CFD for predictive dimensioning of the forces and structural response. Well, what's the good news? The good news is that today, without CFD, we can do even less. Okay, and this ship, most of them are safely sailing the seas, and the combination of the new tools actually gives us hope that we can do better in ship weight, in operating conditions, and all the other things. My fundamental doubt of, well, which waves should I study in order to get deterministic data in order to dimension the ship is still there, and I leave that question hanging in the air. Thank you for your time. Are there any questions?
A quick comment rather than a question. So you made a very good overview about the complexity of the things, about the vessel being on the wave, about the interaction of the energy-saving device with the propeller, and so I think just to add to this complexity, so there is cavitation issue as well. There is a vibration, noise issue. So basically, if you just put this on top of that, that will create like additional layer of the...
Do you know what I call that, Dmitry? Job security.
Yes.
Okay, so thank you. I think there is a question online. Yeah, please go ahead, Merhad.
Can you hear me?
Yes, I can.
Yes, thank you for a great presentation, Professor Jasak. And my question is that, do you think it is possible to investigate each of these complex phenomena separately, then like couple them together? For example, we investigate different behavior of the propeller on different frequency of the inlet wave and load. Behavior of this energy saving device under the effect of different loading of the propeller. Then we say if the propeller behaves differently, we expect this energy saving device to behave this, so we only focus on this specific area, or you think we should do the simulation containing all the issues together?
Okay, you asked me a hard question, so I'm going to give you a nasty answer. I am a poor old CFD specialist who started doing this 15 years ago, saying how hard can it get? And the answer is, it can get really, really hard. So from the point of view of a CFD practitioner, I would like to allow you to do either each element of the system separately, or the entire system with the rotating propeller, energy-saving device, wave, slamming, sloshing, and the other effects. And the closest equivalent that I have for you is the ability of CFD to simulate a gas turbine. So in fact, we can simulate the entire gas turbine, but nobody does it. And the reason why people don't do it is that in order to simulate it, I need to know which one. And if you have finished the design, then the CFD results are just a pretty picture. Okay? So you should think about doing your CFD early and addressing specific questions that are important in the design process at the time. Okay? So the more complex the tool, the higher the cost of the simulation and the fewer of these simulations you can do. Okay? So in gas turbine design,
you can do a lot of your work by looking at velocity triangles, okay? And from the point of view of CFD, they are an illusion. But from the point of view of the design of the actual turbine, they're absolutely necessary. The biggest step in the whole story is validation and verification. I have to prove to you that the pictures that we are producing are actually related to reality. Is that a fair answer?
Yes, I try to capture the answer. Thank you very much.
Okay, thank you. No more? One more question?
So thank you very much. Practicing work also, since I'm seasick, also the movies make me seasick, so they should be realistic enough to my opinion. What about the turbulence modeling that should be used for such kind of simulation?
So there are two problems. The first one is that we are at a very high Reynolds number. And here I'm laughing because we are using wall functions with y plus of the order of 300, 500, 700, which is fantastic because when you do a car, you want y plus of 30. I can't afford y plus of 30. Then there is Dmitriy, the troublemaker, who says this is a rough surface, okay? But we'll figure that out because at such a high Reynolds number, we will have significant effects of turbulence. And to my surprise, wall functions are working great. The bigger problem is something that we have seen about 3 or 4 years ago. And that is related to the fact that we are using single-phase turbulence models in a multi-phase flow. So when you do a sea-keeping simulation, sometimes the turbulence generated on the free surface is so bad that it kills your waves. Okay, and the answer is clear. We need much better two-phase turbulence models which are aware of the presence of the free surface. Okay, but I can see Julien nodding here. There is work at the Danish Technical University, and as people recognize the problem, we are about to get better turbulence models. So far, there is one by Dave Fruman who says, oh, by the way, on the free surface, switch off the turbulence generation term. But that's not great because sometimes it corrupts my hull drag as well. But this is a fundamental turbulence modeling problem that for my satisfaction still hasn't been answered. Okay, so let's stop it here. Thank you for your time again, and let's move to our next speaker.
Excellent. Thank you for the introduction. And actually, I have to start with an apology. So you won't see any ships now in my presentation. Yeah, I hope this is still interesting to you. And I also will try to hurry up to stick to the time and don't stop you from having lunch. So today I will actually give a presentation on a small piece of work of one of our master students at the TU Braunschweig. And the topic, as you can see on the slide here, is the numerical simulation of the wave kinematics near varying bottom topographies. And really, this is more of a teaser of hopefully a lot of work which will be coming in the next couple of months. So the table of content, relatively straightforward. I will kick off with an introduction and then talk about the experimental reference data which we used, and then dive into the numerical model, the results and discussion, and then, as said, dive a bit into the future work and obviously some conclusions. So introduction, as said, no ships in this presentation. But we are sticking to the coastal or offshore world. So what we are wanting to simulate are oyster reefs. And so, as probably a lot of you are aware of the German coast, we have the German Wadden Sea. And here on the top right, you can see a picture of that. So they are relatively significant tidal ranges. And so in some parts of the day, you can see that the Wadden Sea is falling dry. But the Wadden Sea is currently, and this is happening for the last couple of years, really, maybe the last decade, the Wadden Sea is undergoing quite significant changes due to the, and here I called it the invasion of the Pacific oyster. Invasion might be a little bit negatively connotated, which is maybe not quite right. So usually or historically, we had the blue mussel residing in the Wadden Sea. But now, due to climate change reasons, the Pacific oyster is also settling in the Wadden Sea. But actually, the blue mussel, which is significantly smaller than the oyster, and the oyster, they are going into symbiosis. So actually, they live quite happily together. But what you can see here, and this is maybe the picture on the bottom right, and I also have a blow up of this. What you can see is that compared to, for example, a smooth sand surface, these oyster reefs, they form extremely strong bonds and very rigid and rough surfaces. So we've heard about rough surfaces in the very first presentation, but maybe this is a bit of a different scale here. And what is happening because of these rough surfaces is that waves are dampened out. And so now a question in one of our research projects is actually what is driving this damping of the wave, and we want to understand the hydrodynamics around these oyster reefs, doing both experimental and numerical modeling. And as you can guess, in this presentation now, I will be focusing on the numerical modeling aspects of this whole project. And so, yeah, the objective of this work is to develop a numerical model for the analysis of the wave kinematics around such ultra rough bioencrusted surfaces, and really then sort of moving on to understanding the potential to use such ultra rough surfaces for nature-based coastal protection measures. So basically answering the question if it makes sense to basically plant oyster reefs at certain locations to help coastal protection or support the coastal protection. And so with this motivation, we sort of looked at how to model oyster reefs. And I guess this is in principle a very sort of straightforward and standard method. So on the top left here, you see so the field. So we have our oyster reefs. And so from that field data or field observation, we go and build a surrogate, which we test in our wave flume at TU Braunschweig. And then with that surrogate, or from that surrogate, we further want to build a numerical representation. And then probably what's missing here, and this will be mostly part of future work, is sort of the arrow back from the numerical representation to the actual field data. So moving away from the simplified surrogate to actually more realistic representations of the rough surface in the numerical model. But currently we are sort of at this stage here where we take the surrogate and want to build this numerical representation of that surrogate. So talking about the surrogate, let's talk about the experimental reference model or reference data that we used for this work. For those of you who don't know our facilities at the TU Braunschweig, so we have various wave flumes and wave basins, and also we jointly operate the large wave flume in Hanover. But so for these very experiments that we are considering for this work, we used our 2-meter wave flume. And so here on the right-hand side, you can see pictures of the wave flume. So these gray walls here, obviously the walls of the wave flume, and then waves are traveling from the very back towards us. And then we used 6 different surrogate models to represent oyster reefs. So we used half cylinders made out of wood, then lamellas, which are basically very sharp aluminium profiles, and then a mix of the two, where we used the half cylinders and then on top place the lamellas. You can hopefully kind of see this from the schematic representations at the bottom. And then we also considered different spacings of these different structures to investigate the effect of that. Then what did we measure? So obviously the surface elevation. For that we used wire gauge wave gauges. So you can somewhat hopefully see them up here or down here, so very standard. And then also we used ADVs to measure the velocities along the water column. And so in our work now, or in this numerical work, we are sort of sticking to the easiest case of those, which are these half cylinders. So I mentioned we used wave gauges and ADV probes. So this is just another cross-section of the wave flume. So wavemaker here on the left, and then you can see we have quite a significant number of wave gauges. I want to highlight here wave gauge 3, so don't worry about the numbering, that it starts with wave gauge 3. But anyway, so the one nearest to the wavemaker and then the one furthest away from the wavemaker, those are used to calculate the transmission coefficient, which I will come back to in a few slides. And then also I want to highlight this ADV position here. So you can see we measured at 3 different, we measured velocities at 3 different locations. And so the one which I will refer back to in a few slides is the one here, so furthest away from the wavemaker. Last note on this, the total length of the area on which we place our surrogates is 16 meters. So that's a significant length to make sure that whatever flow field develops over the surrogate actually does develop. Okay. Then hydraulic boundary conditions. So in total, in this set of experiments, we tested 3 different waves. So I guess you're all very familiar with this plot here on the right-hand side. So you can see kind of where these different waves lie. So wave period is 1, 2, and 3 seconds. And then we stick to a wave height of 14 centimeters. And those are, in fact, representative of the locations where we actually conducted field studies as well. So representative cases, really. Okay, so moving on to the numerical model. And actually here, it's nothing too crazy, to be honest. So we use OpenFOAM, obviously, version 2012. We use Interfoam for the multi-phase problem. Wave generation is done with IH foam, which I guess you all are very well familiar with. And then maybe one sort of little note here, what we did for wave absorption is that we used a numerical beach. So I put the reference down here. You can see in the equation that it's basically a damping factor added to the momentum equation. And in this paper, we actually showed that it performs very nicely. So that's why we used it here. Interface capturing regular volume of fluid with mules, so no isoad vector or something like this. So very standard. And also flow conditions. So we started off this study considering laminar flow conditions. And I guess in future work, we might want to extend that to include also turbulence modeling. But yeah, nothing too special here, to be honest. And then on the right-hand side here, you can see kind of, I must sort of say here that the case we considered is a 2D case, and this representation is just sort of stretched so that that it's easier to visualize what's happening. So here on the bottom, you can see this representation of these half cylinders from the experimental setup. Right. So just a few sort of numbers regarding the computational domain. So the total length of the area where the surrogate models of the oysters sit, they are similar to the one in the experiment. Water depth, obviously, also similar to the water depth in the experiments, and then the rest of the domain has been adjusted slightly to save computational time, or more so grid size to then save computational time. So that's why it doesn't span the whole or doesn't cover the whole length of our experimental test facility. Numerical beach, you can see here, spreads over 2 wavelengths, so 16 meters, to get good absorption quality of the waves. Boundary conditions, also nothing too special, to be honest. So waves are generated at the left-hand side here on this picture, and then we have the wall boundary condition at the bottom and at the end wall, and then the numerical beach to absorb the waves. The grid. We obviously performed some convergence studies on the grid size and the time step, and we got relative grid uncertainties of less than 2.2%. The overall sort of cell size in this interface region, we worked with 20 L cells per wave height. I suppose using maybe isolate vector, this could be reduced a bit, but anyway, this works for us pretty well. And then, yeah, you can see that we obviously used a body-fitted grid around the half cylinders here. Right, so moving on also for the sake of time to results and discussion. So first off, as mentioned before, we looked at the transmission coefficient. So what we did is with the experimental surface elevation time trace and also with the numerical surface elevation time trace, we did some phase averaging and then computed the transmission coefficient. And here you can see on the right-hand side the obviously transmission coefficient for the flat surface and the half cylinder surface, or so rough surface. So we did include the reference case here. And so these are the results for the 1 second wave, then for the 2 second period wave, and for the 3 second period wave. And you can see that for the flat bottom, we actually get pretty good agreement between experiments and numerics. And then for the half cylinders, dependent on the period, we get bigger or smaller deviations. So a maximum deviation actually of around 12%, which is still okay. But as you will see later on, there is some potential to improve this. But generally, for what this is, we were relatively happy with those results. And then moving on to the velocity counters, I guess those are the more interesting results. So what do you see here on the right-hand side? So in the first panel, and this is now for the reference case, so flat bottom and a wave period of 2 seconds, you can see the phase averaged free surface elevation. The dashed blue is the numerical and the dashed red is the physical result. And then below that, we have the phase averaged velocities over one period, and then the panel in the middle is for the physical experiment, and then the panel at the bottom is for the numerical, or from the numerical results. And yeah, so this is, as I said, for the reference case, so flat bottom. And then if I flick on one slide further, you can see that it changes. So this is now for the rough bottom topography. And yeah, first off, apologies for this lack of data here at the bottom, but I guess that's what happens if you work with physical experiments. So there's something going on with the data here. But anyway, what we can see is that first off, and now I'm sort of quickly flicking back and forth again. So first off, we can see that the change in the free surface elevation is minimal. But then moving from the smooth surface, so this one, to the rough surface, we can actually see that there's quite an increase in the velocity magnitude. And what is sort of most important here is that qualitatively we get quite a good agreement between the numerical model and our physical results. So then moving on to the wave period of 3 seconds. And if you recall our transmission coefficient there, we were able to see quite some significant differences. And this sort of also holds now for the surface elevation. If we look at this plot up here, so again, dashed blue is the numerical data, and then dashed red is the physical data for the reference case. And here we can see that there's quite a bit of deviation which we need to sort out. But again, sort of the qualitative agreement of the velocity magnitude close to the bottom is actually pretty, or matches pretty well. And then we sort of flick on to the rough bottom topography, and there we can see that we get a slightly better agreement in the free surface elevation. But then again, what's sort of most important for this study right now is that qualitatively our agreement between the experimental and the numerical velocity profiles, let's say, is really good. So that encourages us to sort of continue this work and extend the model. And so that's actually maybe a good segue to quickly move on to conclusions and future work. So conclusions, yeah, obviously this is a first step towards modeling the wave kinematics near rough bottom topographies. I guess you all agree that our surrogate with half cylinders is a very simplified model of what you've seen in the first slide, so the actual oyster reef. But as said, this is a first step, so it encourages us to continue our work. We get relatively good agreement in terms of transmission coefficient, so as said, less than 12.5%, which is sufficient for what the model is right now. But then we do see some artifacts in the free surface elevation, especially for this 3-second wave, which we might have to investigate what was going on. But sort of most importantly, and this is really sort of what I want to tease you with, is that we do want to obviously extend our model to be able to include these sharp lamellas, because I can tell you that, as you probably guessed, those have the more significant influence on the velocity profiles and the wave attenuation in our experiments. But then, and this is really exciting, and I hope that we will make some good progress there, we also want to extend our models or our model towards modeling an actual oyster. So we want to take 3D scans of an actual single oyster, and then potentially also an oyster reef, and chuck that into our OpenFOAM model to then really get a better understanding of the actual hydrodynamics in the field, rather than comparing to models as we are doing right now. And so I hope this wasn't too quick, but anyway, thanks a lot for your attention. Just a quick acknowledgement of our funding agencies. And if you have any questions, then feel free to ask them now, or in fact contact me on the app or on LinkedIn or wherever, and then I'm happy to answer any questions. Thank you.
Thank you very much, Christian, for this excellent work. Are there any questions in the room?
So thank you very much for your presentation. I have just a quick comment. So at the very beginning, you said it's not very related to the maritime business and the ship business, but at the same time, I not fully agree with this statement, because obviously on the ships, we don't have the oysters, but we have barnacles, which are connected to the vessel. So, and this, it's a quite a painful experience both for the ship owners, because it's actually increased the energy consumption and the fuel consumption, and obviously for us, for the researchers, we don't really know how to address this challenge. So basically, your work, even it's not particularly related to the ships, it's actually quite important for us as well. So yeah, I would like to follow, you know, your future work, and good luck with this. So thank you very much for that. It's just a quick comment.
Excellent. Thanks for that.
Thank you. I will ask you a couple of questions, if you don't mind. So the first one is, do you have any facility for measuring turbulence during wave impact in the tank?
So what we do have is, so PIV was mentioned earlier. And so what we have on site is now a PTV measurement device, so particle tracking velocimetry, which enables us to measure velocities on a volume. So it's basically a shoebox size volume which we can measure. And there the frequency is really high. Now, unfortunately, I don't know the number off the top of my head, but sort of compared to regular PIV, our frequency, measuring frequency is higher. So that might enable us to look more into sort of turbulent effects happening in the marine, coastal, offshore environment. I'm not quite sure if that is a sufficient answer to your question.
Thank you. It's enough for the moment. So the second question is related to the oysters themselves. From what
Yes.
I can see from numerical and experimental data, they actually help because they increase the dissipation of wave energy. Okay, so
Exactly,
what
yeah.
I wanted to ask you if they are edible as well.
Very good question. I think the ones in the Wadden Sea I wouldn't eat. I think they just, because of their filter action, I think whatever they filter out of the ocean might not be good for your health. But quite technically, I think you can eat them. But you may be better off using ones from aquaculture rather than the field.
In that case, Christian, you can grow some in your wave tank and we'll come and visit you. Thank you very much. Are there any other questions? No. In that case, thank you, everybody. Thank you for all the presenters. This is the end of the current session. Goodbye.